This is APAB Calc. We are still doing section 1.2, and we're talking about limits graphically. So we're picking up at P1. We just did an E1 in the other video. And just like in the other video, this is a fairly long example, or fairly long practice problem, just like that example was pretty long. So if you feel confident that you know how to do this based on what we did in E1, you should just pause me and give this a try on your own, and then check and see if your answers line up with my answers. So I'm going to walk you through those. So I picked a bunch of random x values, right? What I did here is I picked a couple that are nice, happy, continuous points, and I picked all of the ones that are not nice, happy, continuous points. So we'll walk through. But remember, if something is continuous, then all four of these values are just equivalent to whatever the y coordinate is of the actual point. So we're going to go ahead and start with a equals -5. So right here, here's the spot where x would be -5. And you can notice right away that that's weird, right? Like there's this weird, this hole with sort of a lid, right? So what I notice here is as I approach x equals -5 from the left, right, the left guy, I'm approaching a y value of 2. And as I approach x equals -5 from the right, I'm also approaching a y value of 2. So what that means is that my left-sided limit is an output of 2, and my right-sided limit is an output of 2. And since they have the same number, my double-sided limit is also a 2. And at the end of this video, we will talk about those rare instances where there is no double-sided limit, not because it doesn't exist. Well, let me rephrase, where the double-sided limit inadvertently is a single-sided limit. We'll talk about that in a little bit. And then the last thing to note, though, is that the actual y value at x equals -5 is a 1, right? So this is going to be a 1. So this is not a continuous point because not all four of these line up, right? Now let's look at x equals -4. So here's the line where x is -4. You'll notice that this is a nice, happy, continuous point, right? The second I see that this is a nice, happy, continuous point, I can answer all of these values as whatever the y coordinate of the point would be. So this is a nice, happy, continuous point where I didn't have to lift up my pen, and the y value of that point is a 1. So all of these are a 1. And you can see that by actually drawing approaching from the left of -4 and to the right of from the right of -4, and that's the double-sided limit, and it's also the dot that is the closed circle. But again, it's easier to just recognize that if you look at a point and there's no discontinuity visually, then all four of those values should be the same. Now let's look at x equals -2. So here's where x is -2, and this is definitely another spot where a lot of weirdness is happening. So the guy just to the left of -2 is approaching this y value of -1. The guy just to the right of that line where x is -2 is approaching a y value of 4. So first off, my left limit is a -1. Then my right limit is a 4. Because these two numbers are not the same, the double-sided limit does not exist. And then the closed dot is actually neither of those two spots. The closed dot's actually at 2, so all of those have different numerical values or answers, because D and E is not a numerical value. Now let's look at A is 0. So here's the line. It's the y-axis where my x is 0. You'll notice that this is a nice, happy, continuous point, and the y value is 6. So I don't have to go through tons of work. I can just recognize that's a nice, happy, continuous point, and the y value of that point is 6. At 1, I get more weirdness, right? So here's the spot where x is 1, right? The guy to the left of 1 is approaching a y value of 7. The guy to the right of 1 is approaching a y value of 4, right? So I have a 7, a 4. Because those two numbers aren't the same, I'm going to have D and E, or does not exist. And then the closed dot is at the 7, right? So that's where the actual function's value would be. 2 is one of those nice, happy, continuous points, because here's where x is 2. And sure enough, right there is a nice, happy, continuous point with a y value of 3. So all of my answers are 3. And you can walk through them individually, or you can just recognize that it's continuous. When I look at x equals 3, there's a hole, right? So because this hole exists, the left-sided limit and the right-sided limit are actually going to be the same, but there's no actual value for the function. So what's going to happen is I'm going to get that the left-sided limit is a 2, so is the right-sided limit, which means the double-sided limit's a 2, but there's no actual value for the last part of the answer because the function is undefined, right? It is not, it has no definition. It has no defined value at that point because there's no input, so there's no output. If we look where a is 4, we're going to get another weird point. So here's my x equals 4, right? So my left-sided limit is going to be that positive 1. Just to the right of 4, I'm walking down to this point, which will be a negative 4. Sorry, computer zonked on me. All right, so we have a positive 1 and a negative 4, which means that the two guys are not walking to the same point, so my double-sided limit does not exist, and the closed dot is at 1, so that's the y value of the actual function. And the last one we're going to do is at 5, and there is some weirdness at 5. So 5 is similar to 4 because we have the left-sided guy down here is walking a negative 3. The right side guy is walking up to 1. So my left-sided limit is a negative 3. My right-sided limit is a positive 1, which makes the double-sided limit does not exist, and the closed dot happens to be at the 1. So those are all my values. Now, what I said we would discuss at the end of this video is what happens if there is no double side. So let's talk about the double-sided limit in a sort of unique situation. So usually to find the double-sided limit, you're going to evaluate the left and right limits and compare them. But let's get rid of my P1 and let's do a different example. Let's say I have a graph that only exists from negative 1 to 3. All right, so let's say I have a graph. Okay, so that's my y equals f of x, and it's a terrible graph, but you get the idea. Now, what's tricky about this graph is that this graph literally only exists from negative 1 to 3. There is no graph after the x value of 3, right? There is no value after 3. So, the thing is that if we look at this spot, okay, if I asked you for the limit, so I can't ask you, not just me, like an AP or anyone else, can't ask you for the limit as x approaches negative 1 from the left, because there is no left, right? There is no left of negative 1 in the domain, right? The graph is literally not defined anywhere over here, and I also can't ask you for the limit as x approaches 3 from the right, because again, there is no right of x equals 3 in this domain. The graph just straight up does not exist after 3, right? So what that means is that in this really unique situation, like in this special situation where there is nothing to the left of negative 1, so the double-sided limit as x approaches negative 1 of f of x is just equal to the right only, right, to the right side limit, because there is no left. So the two sides, left and right, can't be equal because there is no left. So in this situation, the double-sided limit would just be equal to the only side that there is, which is in this case right, and it would be a value of 1, right? The same thing would be true over here. There is no right, right? So there is no right of this spot. So here, the double-sided limit at x equals 3 would be equal to the left limit only. So for example, in this particular case, the limit as x approaches 3 of f of x, which would be the double-sided limit, would just be the same as the left limit because there is no right. So you can't compare the left and right limits. You just have to make it the same as the left limit, which is a 2. Okay? So in general, the way you find the double-sided limit is by comparing the left and right numbers. If they're the same, that's your double-sided limit. If they're not, your double-sided limit does not exist. But in the rare case where you're looking at an endpoint, right, if you're looking at an endpoint so there is nothing past that point on the graph, then you would be looking at a situation where there is no right, there is no left. You only use the one limit that you have. Now, just to make the distinction here, if I had changed, right, so if instead I still have this point at 2, but I make this an arrow, well then none of this is true. There is a right now because you could be to the right and to the left, right? So the difference is a hard endpoint, right? And it could be an open endpoint, it could be a closed endpoint, it doesn't matter. It doesn't matter if it's open or closed, but the simple idea is that the graph literally ends at that point. There is nothing past it, okay? A really common example of that, if you're thinking, okay, cool, Hogan, but you keep making up these crazy examples, which is true, I do. But let's say I wanted to give you a really common example of something that has a defined endpoint. What if you're graphing the square root of x? This has a clear endpoint, right? This has a clear endpoint at x equals 0. So if I wanted the limit as x approaches 0 for this function, right? So we'll call this f of x, right? If I wanted the limit as x approaches 0 for f of x, it would be the same as the right-sided limit because there is no left, and it would be a 0. Okay, so that's what I mean. So there are graphs that have clear endpoints. Not every graph does, but there are graphs that do. And so if you have a graph that has an endpoint, it doesn't have to be a crazy graph that I make up. It could be a pretty common graph like the square root of x. That's the idea, okay? So that's sort of what we're going to do with limits graphically. That's about it. What we're going to proceed to in our next video is we're going to start talking about limits algebraically and how we evaluate them using algebra when we're given an expression.